Good morning, students. Chapter 7, System of Particles and Rotational Motion. Yes, it is one theory which is based on law of conservation of angular momentum. Yes, we know that. What is law of conservation of angular momentum? Okay, if dot is 0, then total angular momentum is constant. Okay, so yes, we have to apply this law in Kepler's second law of planetary motion, which is based on law of conservation of angular momentum. Kepler, yes. Next chapter is gravitation. We will study gravitation. Okay, there are three laws of Kepler. First law, okay, all planets are revolving around Sun in elliptical orbit. Okay, yes. And second law that we will prove here. Okay, what is second law? We will prove here, but before that, first statement, that is, if here it is Sun, here it is Sun, then all planets are revolving in elliptical orbit around Sun. Okay, so it is elliptical orbit. It is elliptical orbit. Okay, let planet is here. Planet is here at this point. Let planet is here. Okay, at point X. At point X. Okay, it is line joining Sun with planet. It is line joining Sun with planet. Okay, here it is planet. Okay, so yes, now we know that, okay, on its path, direction of linear velocity is in direction of tangent. So if it is revolving in this direction at this point, direction of linear velocity, it is in direction of tangent. So it is direction of velocity. It is direction of velocity. Clear about it? Okay. If mass of this planet is m, then its linear momentum, that is p, it is also in direction of velocity, because we know that v is equal to it is m. Because we know that p is equal to it is m. Clear about it? Okay. Okay. So yes, here it is planet, Sun. Its velocity of planet, it is in this direction, its linear momentum in this direction. Okay, now I will find angular momentum of this planet with respect to Sun. So first of all, I will write data like this. Okay, as shown in figure, planet is revolving in elliptical orbit, at point X. Its linear velocity is v, and its linear momentum is p is equal to m, where m is mass of planet. M is mass of planet. Okay, where m is mass of planet. Now we have to find what is angular momentum. So yes, here I will write angular momentum of planet with respect to Sun. We know equation of angular momentum. Yes, here it is. See, I will write here the angular momentum. Okay, angular momentum. Angular momentum. Angular momentum L is equal to, it is R cross P. Okay, so L is equal to, it is RP sin theta, or you can write L is equal to, it is R P. P means here it is MV, and here it is sin theta, where theta is angle between R and P, where theta is here angle between R and P. Clear about this? Okay. Here what happens? See, we have to find angular momentum. So angular momentum, how to find? So yes, L is equal to, it is R cross P. L is equal to, it is R P sin theta. L is equal to, it is R and V sin theta, where L is mass of planet, V is velocity of planet, and R is perpendicular distance. And R is perpendicular distance. R is perpendicular distance. So see how to find this one. Okay, perpendicular distance. So for that, draw line of action of V. Line of action of V. Okay, and from this sun, draw one line which is normal to this line of action of P. This line of action of P. So yes, it is called perpendicular distance B. It is called perpendicular distance B. Clear about this? Clear about this? Okay, let this distance is S. Let this distance is S. Okay, so yes, here perpendicular distance of this linear momentum, perpendicular distance of this linear momentum from this sun is D. Then how to find angular momentum of planet? Angular momentum of planet L is equal to linear momentum P into perpendicular distance, that is D. Linear momentum P into perpendicular distance T. Yes, I have considered perpendicular distance means angle is equal to 90. 90 angle sin 90 is equal to 1, that is RP, P, linear momentum, and R is distance. Okay, so yes, angular momentum of planet with respect to sun, L is equal to, it is PD, P is equal to, it is MV, so it is MVD, equation number 1. It is equation number 1. So angular momentum of planet with respect to sun, L is equal to linear momentum into perpendicular distance is equal to, it is MVD, equation number 1. Now see here in this figure, see, it is line joining sun with planet. See, it is line joining sun with planet. It is perpendicular distance of linear velocity with respect to sun. So see, from figure it is clear. From figure it is clear. It makes some area. Here it is. It makes some area. Yes or no? Yes, it is. It makes some area. Yes, it makes some area. So here in this right angle triangle, okay, as shown in figure, line joining sun with planet, as shown in figure, line joining sun with planet makes some area, and let that area A is equal to, you know its equation, area is equal to base into height. Okay, half base into height. Base is D and height is S. So yes, it is D into S. Clear about this? So as shown in figure, line joining sun with planet makes some area. Now, important one. Planet is moving. It is revolving. Planet is revolving. So yes, I have assumed K. Initially, it is at point X. Now, as it is revolving, after some time, it will be here at point X dash. It will be here at point X dash. Okay, after some time, some time. Let planet is at point x dash. Let planet is at point x dash. Clear? Okay, after some time, let planet is at point x dash. Then what happens? Then now in this case, what is line joining? Line joining planet with sun. Yes, it is this line. Yes, it is this line. So see what happens. What happens? It is the perpendicular distance d. It is the perpendicular distance d. Yes, it is the perpendicular distance d. Okay. Initially, planet was here at point x. So it is area made by line joining planet with sun. Now as planet is moving, and here it is at point x dash. Then see, this much area is increased. It is increase in its area. It is increase in its area. In short, there is change in area with time. There is change in area with time. There is change in area with time. Clear about this? Clear about this? Okay. So here, as there is change in area with time, I will find rate of change of area. Okay, and how to write this? See here. Okay, after some time, let planet is at point x dash. So from figure it is clear. From figure it is clear that area swept by line joining planet with sun changes. Simple. Okay. From figure it is clear that area swept by line joining planet with sun changes. Okay. So now I will find rate of time rate. Now I will find time rate of change of area swept by line joining planet with sun. Okay, time rate of change of area swept by line joining planet with sun means its time rate. So dA upon dt is equal to, here it is d upon dt of, here it is 1 by 2 d into s. Now see what happens. Okay, you have to observe this thing from figure. Okay, so see from figure, the initial area is this paint one. Okay, it is D and it is S. Yes or no? After that, after some small time, yes, it is small time. Time rate of change of area swept by line joining planet with sun for small time. Okay, so yes, planet is here at point x dash. So see, now the new area is this one. See, in this area, what is here? D is same. There is change in S. Yes or no? Yes. It is triangle. See, it is triangle. Its equation is half base into height. Base is same. Only height is changed. Means only this distance S changes. So how to write this? Therefore, dA upon dt is equal to half d constant. It is d upon dt of s. Yes or no? Okay. And then see, this s distance is along this line. Then ds upon dt, rate of change of distance or position with respect to time. Rate of change of position with respect to time. It is called velocity. So here it is nothing but half dV, because ds upon dt is equal to v. Clear? Okay. Now both sides I will multiply with m. Therefore m dA upon dt is equal to half m d. Now see, m dt is equal to, it is L. So therefore dA upon dt, m dA upon dt is equal to, it is half L. So therefore dA upon dt is equal to, it is L upon 2m. dA upon dt is equal to, it is L upon 2m. Now 2 it is constant. M, that is mass of planet, it is also constant. So what about L, that is angular momentum? See here in figure. Which type of force is acting between planet and sun? Gravitational force. Again, which type of force acts between planet and sun? Gravitational force. And gravitational force acts along the line joining two objects, means planet and sun. So on this planet, if gravitational force is acting, that gravitational force is acting along the line joining planet and sun and towards it like this. So it is gravitational force acting. It is gravitational force acting on planet. And see, as this force is passing from sun itself, about which you have to find angular momentum, then you know that if line of action of force passes from the reference point, about that point torque will be 0, and if torque is 0, then angular momentum is constant. Okay, here I will write, here line of action of gravitational force acting on planet passes from sun. So therefore, with respect to sun, torque on planet is 0, and if torque is 0, therefore angular momentum is constant. So see in this equation, 2 constant, m constant, so L is also constant. See, angular momentum is constant, L is also constant. So I can write this as, therefore dA upon dt is equal to constant. dA upon dt is equal to constant. And this dA upon dt, it is called aerial velocity of planet. Clear about this? So yes, it is one important point that you have to remember. Aerial velocity of planet, dA upon dt, remains constant. Aerial velocity of planet remains constant. Now what is its statement? Yes, I will write its statement. See, here it is. See, area swept by line joining sun with planet in unit time is constant. Area swept by line joining sun with planet in unit time is constant. Means in same time, area enclosed by line joining sun with planet is same. Clear about this? So yes, dA upon dt, that is aerial velocity of planet, is constant we can prove this thing only if L is constant, that is angular momentum is constant. Clear about this? So yes, it is again one important theory. Okay, and yes, this equation you have to remember. Okay, dA upon dt is equal to constant, dA upon dt is equal to is L upon 2m. Yes, this above equation you have to remember to solve some MCQs. Where L is angular momentum, 2 is to, and m is mass. L angular momentum, 2 is to, and m is mass. So yes, dA upon dt, it is called radial velocity of planet. It remains constant. It remains constant. Clear about this? Okay. So yes, it is one important theory, that is Kepler's second law of planetary motion. This statement is called Kepler's. This statement is called Kepler's second law for planetary motion. Clear about this? This is it for today.